We're now going to continue the discussion on infinite series with positive terms by looking at a category of series called p-series. P-series are series that have the following form. Note that p is a constant. What we're going to do now is determine the values of p where the series converges and where the series diverges. Let's begin with p less than 0. In this case, the nth term an is equal to, and we can now test if the series diverges using the test for divergence by looking at the limit as n approaches infinity. And this limit is equal to infinity because p is less than 0. Therefore, in this case, the series diverges by the test for divergence. We now analyze the series when p is equal to 0. In this case, the nth term is equal to, and if we take the limit as n approaches infinity, we get, which is different than 0, therefore the series diverges by the test for divergence. We now look at what happens when p is greater than 0, and the nth term is equal to, and the limit as n approaches infinity is equal to, so it's equal to 0 because p is greater than 0. So in this case, using the test for divergence, all that we can say is that the series may or may not converge. And to determine if the series converges, we use the integral test, and I'll leave that step up to you. The following theorem tells us for which values of p the p-series converges, and for which values of p this p-series diverges. So we see that when p is greater than 1, the p-series converges, and when p is less than or equal to 1, the p-series diverges. Let's begin by looking at a series that we already know that falls within the category of p-series, and which is the harmonic series. For this series, the value of p is equal to 1, and therefore by Theorem 6, the series diverges, and this confirms what we had found previously about harmonic series using the integral test. And let's now continue with the following examples. In A, we note that we have a p-series and the value of p is equal to 3. Therefore, p is greater than 1, and we say that the p-series converges. In B, the value of p is equal to 0.8, and 0.8 is less than 1, therefore the series diverges. Example C is a harmonic series, and we already know that the harmonic series diverges. And in example D, we have a p-series, and p is equal to 1.5, which is greater than 1, therefore the series converges. We're now going to look at another test for determining the convergence or divergence of a series, and this test is called the comparison test. And we can understand this test with the following graph. So what we see is that we've got two series. The first series is the one with a terms, and the second one is the series with b terms. And what we see is that the b terms are always greater than the a terms. And what we can say is that if the series with b terms converges, well then so does the series with a terms, because the b terms are always greater than the a terms. And we can also say that if the series with a terms diverges, well then the series with b terms will also diverge, given that the b terms are always greater than the a terms. And this here is explained in the following theorem. So it's the theorem for the comparison test. And what this theorem says is that, well, if you've got two series, one with a terms, the other one with b terms, and if the series with b terms is convergent and an is always less than or equal to bn for all n, well then the series with a terms is also convergent. And if the series with b terms is divergent and an is greater than or equal to bn for all n, then the series with a terms is also divergent. We're now going to look at an example of the comparison test. So determine whether the following series converges or diverges. We begin by writing out the nth term of this series, which is. We now compare an with a similar term, which I choose to be the following. Note that when n is large, the values of an are very similar to the values of bn. Also, an is less than bn for all n. This is because of the number 5 on the denominator, which makes the denominator of an slightly greater than the denominator of bn. Hence, the values of this expression will always be less than the values of this expression. We now look at the series with the nth term bn and analyze the convergence of this series. And what we see is that we have a p-series, and the value of p is equal to 2, which is greater than 1, therefore this series here converges. And given that bn is greater than an for all n, we can say that the series with nth term an also converges by the comparison test.